My name's Kelly Hambleton, and I'm here to talk to you about heartbeat stars. But first, let me mention that I'm working with a group of people. So that includes Don Kurtz and Susan Thompson that are here in the audience, and also Andre Persha and Jim Fuller. So heartbeat stars have been theorized for a couple of decades now, and it's not until we had space missions such as Kepler and CoRoT that we actually started to see these objects. So what are heartbeat stars? Heartbeat stars are essentially eccentric ellipsoidal variables. So ellipsoidal variables are binary stars that are rotating around each other, and as they do so, you see different aspects of the star. So here at the bottom, you can see an essentially teardrop shape. So when we see this teardrop shape from a side-on view, we're seeing a larger surface area, and that means we get a peak in the light curve, whereas when we're seeing it at more of a point view, then we get a dip in the light curve. Now, this is an image of an eccentricity equals 0 ellipsoidal variable, but what happens as the eccentricity increases is that we start to see different shapes in the light curves, also dependent on the argument of periastron, or the phase of closest approach relative to the observer. So these shapes become stranger and stranger as the eccentricity increases, and this brings me nicely on to heartbeat stars, which have a very high eccentricity. So John introduced heartbeat stars nicely for me before and showed the heartbeat star that you can see at the top of the plot. This is KOI 54, and this is a very interesting system because it shows, as John said, both the 90th and 91st harmonic, which are very highly excited, and then some other harmonics that are also excited. So we see a range of these objects, including red giants, which there is a very nice poster on, poster 101, that's Paul Beck's poster, if you want to go and see that. We also see main sequence stars with the primary component from G to A-type stars usually. And then a whole range of objects with spots, some with eclipses. The only one with an eclipse here is this one on the bottom, well, on this panel here. The little blip that you can see is the eclipse, whereas the rest of the dips are due to the eccentric ellipsoidal variable nature. I'd also like to say we have now found in the Kepler sample 156 of these objects, so we do have a very large sample, jugs and jugs, some might say. So a lot of these objects show something called tidally induced pulsations, so approximately 20% in the sample that we found so far show this phenomenon, and that is pulsations at a precise integer multiple of the orbital frequency. So that means you could get, for example, 5 pulsations every orbit, or 10 pulsations. And these are pulsations that are forced by the tides. So all of these pulsations have an L equals 2, M equals plus or minus 2, or 0 mode. And the way that we can easily identify these is that they phase accurately, precisely with the light curve. So in a phase light curve, you'll still see the pulsations. So these were hypothesized by Zahn as a method for mode damping to remove the energy from the orbit, but also by Kumar as the dynamical tide aspect to the heartbeat stars that he theorized in 1995. So we can look at the amplitudes of these modes to try and understand something about the radii of the stars, because the amplitudes are determined mostly by the ratio of the radius to the semi-major axis, and also the phases of the pulsations relative to the argument of periastron are dictated by the azimuthal order of the mode. So there is also a new theory on something called, well, relatively new theory on something called resonant locking. So that is where we have a mechanism at play where as the orbit evolves and you have the exchange of angular momentum between the star and the orbit, this causes the stellar eigenfrequencies to change. So you have the natural eigenfrequencies of the star changing along with the period of the star changing. Now, as I mentioned before, tidally induced modes are induced by the orbit, and they are multiples of the orbital frequency. So if the orbital period is changing and also the eigenfrequencies of the stars are changing, this can cause a locking of the tidal modes in a resonance, which means that where we wouldn't usually see very many resonant modes, so very highly excited modes, because they will pass through the resonance quickly, this resonance locking theory suggests a mechanism by which the modes will be caught in resonance for extended periods of time, actually allowing us to see them. So this has some predictions. It suggests that this wouldn't occur at low frequency modes because they are traveling waves. It suggests that they wouldn't occur at high frequency modes because there's low mode energy associated with the high frequency modes. And it also has predictions for the amplitude based on the stars, the stellar parameters themselves. So KOI 54 was suggested to have the 90th and 91st harmonic with a high amplitude because of this mechanism. However, now we have found another example to suggest that resonant locking really is the case. So KIC 8164262 is the object that I'd like to bring your attention to. It's an A star and an M dwarf in an approximately 90-day orbit with an eccentricity close to 0.9, with a stellar mass of 1.9 for the primary and approximately 2.21 for the secondary, and a primary radius of 2.5 solar radii. And I'd just also like to bring your attention to the very strong tidally induced pulsations that you can see in this light curve. Well, there is one in particular that has a very high amplitude, and then this dip here is actually the heartbeat star itself, so the static tide. So the first thing we did was to obtain spectra. We've obtained 2 spectra for this object at Kip Peak, and usually you would apply TOD-CORE, which is a 2-dimensional cross-correlation program to determine the radial velocities of the stars. So what we did, instead of just using it in the normal way, we combined it with emcee, which is an affine invariant version of Markov chain Monte Carlo. And doing this, we were able to interpolate between the spectra and fit the spectra simultaneously while obtaining the radial velocity results. And by doing this, we were able to get posteriors on all our effective temperature, log G, metallicity, V sin I, and the radial velocities for both nights. Once we had these radial velocities, we went on to model the binary features and the stellar pulsations. Now, again, we did this using Markov chain Monte Carlo simulations, but we chose to do this simultaneously. So we simultaneously fit not only the light curve and the binarity features, not only the light curve and the radial velocity, but also the pulsations in the light curve. As you can see as well, we got quite a good fit to the data, with the residuals being very low. So I did mention that this had one very strong pulsation peak, and here you can see the light curve, the full light curve of the binary star, an FT of the full light curve, and this shows that the one peak is approximately a millimag. If I remove this peak, you can see that there's essentially nothing left in the light curve, in the Fourier transform. But then if we zoom in, you can see that there's still quite a bit of information, just a lot smaller amplitude. So most of these peaks are actually tidally induced pulsations, so multiples, exact multiples of the orbital frequency. But then we have these 2 that I've highlighted in red that aren't multiples of the orbital frequency, however, are harmonics of each other. So that suggests that this is rotation. And of course, we have the rotation, the V sin I, from the spectra themselves. So now we can compare the V sin I and the rotation of 3 days that we get from these peaks. And we found that they weren't precisely matching. Now, this is suggestive of one of 2 things. Either the star is rotating differentially, or the star is rotating obliquely. And it would have an obliquity of 21 degrees if that was the case. Now, as I say, we can have theoretical predictions for these resonantly locked modes. Now, in this diagram, across the bottom, we have the harmonic number of the pulsation. On the y-axis, we have the amplitude of the mode. The stars represent all the modes found in this object. The dotted line represents the highest amplitude mode that you can get for forced pulsations, tidally forced pulsations. And the solid line represents the average amplitude of the forced pulsations that you would expect. Now, here you can see these 2 points are the points from the rotation that I mentioned earlier, but the rest are all what we expect to be pulsations. They're all harmonics of the orbital frequency, and you can see here that this one lies on this red line, which is the prediction for tidally locked mode. So the red line is a tidally locked mode that is where the frequencies are increasing with the orbital evolution, whereas the blue is for the frequencies that are decreasing with the orbital evolution. So I'd like to just draw your attention now to another object that we're working on. This is a more preliminary work, but this is another interesting object. It has all the modes that we find in this object are tidally excited, and it's a late A and an early F component, so we would actually expect to see natural pulsations, which we don't. It's a period of 20 days, and the time and the pulsations are essentially overlapping, well, they're very close to the orbital features of the star. Again, it's highly eccentric, and it also has very strong apsidal motion, which is something that we tend to see a lot of in these objects, and it's something that there is quite a bit of theory on as well. So this is a Fourier transform of this object. This time the pulsations are highlighted in blue here. This is the kind of Fourier transform that's a lot more similar for what we see in most of the objects with tidally induced pulsations. You have this power peak that is due to the orbital characteristics. I've subtracted the binary features, so the purple is the complete Fourier transform. When I subtract the binary features out of the light curve, you're left with the green. And then I pre-whitened from 0.5 cycles per day, so that we could just focus on this blue hump of power here. And these are what we believe are the tidally induced pulsations. So you just get a peak of several pulsations. And actually, when I extracted them, there are 7 pulsations there. So this is the radial velocity curve for this object. As you can see, it's a nice double-line spectroscopic binary. And again, what we did was we started to fit the pulsations and the binary characteristics and the radial velocities all simultaneously. And we did this by adding 1 pulsation at a time to see how this affects the light curve. So we haven't quite finished. We still have some way to go. But from what we've determined, it doesn't seem that adding the pulsations really affects the best fit and the parameters of the binary star that significantly. So this is good because many people model a binary star by modeling the binary features, subtracting that, and then looking at the residuals. And this is just suggestive that that won't have a very large effect on the parameter values that you're obtaining. So in conclusion, with heartbeat stars, we're able to determine fundamental stellar parameters, as with most binary stars. But evidence suggests that resonant locking can be the cause of us being able to see these resonant pulsations. And it's not only now in KOI-54, but we also found it in another objects. So we also determined that the phases relative to periastron give us information about the azimuthal order of the modes, and that tidally induced modes appear to affect apsidal motion. This is certainly something that we want to follow up on. And in the future, we would like to study the orbital evolution of the stars and really try to learn something about the gravity darkening of these objects, because it's a very key feature in these light curves. Okay, thank you.
Thank you, Kelly. Comments or questions? Mark?
One of the really difficult and interesting questions in tides is the dissipation rate, the tidal rate Q, and it seems like these would be excellent systems for studying that. Can you say anything about that, the dissipation timescale?
Well, one thing that we would look for, or we have been looking for, is a change in the eccentricity. So far, we haven't determined that, but it takes quite a long time to model each system individually, so we're certainly looking for that, but haven't found it yet.
Laszlo?
Do you have examples when you can suspect that both stars start ringing after the periapsis?
Actually, for KOI-54, it is theorized that both stars are pulsating. They're very similar in both mass and radius.
I mean the last of your examples also, I mean, that from the radial velocity curve, they must have similar masses.
They're very similar. Well, we haven't got to the stage yet where we're disentangling the pulsations and really looking at that aspect. But I know with KOI-54, the 90th and 91st harmonic, they believe, come from the different stars.
Thanks, Kelly. You said several times that the induced oscillations are exactly multiples of the orbital frequency, but in the real world, nothing is exact. So can you measure differences from exact multiples, and if so, what does that tell you physically?
The pulsations are very precise to a high percentage. We really haven't seen anything that suggests that the differences would be caused by anything. I haven't looked into that, but they're very precise, so it would be hard to see that.
Before I take another question, I'd like to respond to that. That in the real world, the frequencies are exactly the same because one drives the other to that. You actually drive the frequencies. Someone else way to do that.
Sure, but eventually there'll be a disagreement. At some precision, there must be. Well, you have a pulsation frequency and you have an orbital frequency, and the claim is the ratio of those two is exactly an integer. And all I'm saying is that at some level, and maybe it's 10 to the minus 100, they'll differ. And I just wonder what the physics is of that. Sure.
Yes, I wanted to know what, it's me.
Oh, thank you.
What makes you thinking that the gravity darkening is important? Is it the true rotation of the star, or is it the importance of the tidal distortion?
So the feature in the light curve is dictated quite strongly by the presence of gravity darkening. I mean, these objects generally don't rotate too fast from what we've seen, but they rotate fast enough that gravity darkening has a significant presence in the light curve.
Okay.
Zvi, did you try to see, as we heard this morning, did you try to see a shift in the frequency because of the motion?
Yes, we have. We've been using, Simon actually looked at one of our stars for us not very long ago, and he did find that, yes. We also applied the frequency modulation method, which is essentially the same thing, but looking in the Fourier Transform. And yes, we do. For that one prominent peak, we do find that exact thing, yes.
If I may take advantage of that question, Zvi, Kelly and I and some others are just about to finish a paper where we show that those techniques work in an eclipsing binary so that you can see that we get the same answers as you do from your traditional techniques, so that you will trust us in the future. And we'll give that to you very soon.
I trust you, Dawn, from ever.
Right, could we thank Kelly for that once more?